we're going to look at dicarbon dichloride molecule using the valence bond theory. And the valence bond theory states that a bond forms between two atoms when orbitals overlap and a pair of electrons occupy the region between both nuclei. So before diving into the structure of the molecule, I'm going to show you guys the molecule with the atomic orbitals and where the atomic orbitals overlap. So in the top one right here, you'll see that the atomic orbital, it's just the atomic orbitals, and on the bottom ones you'll see where the atomic orbitals overlap, and that's going to be right here between these, the carbon orbitals and the chlorine orbitals, and between the two carbon orbitals. So we're going to start off with the Vesper diagram, and so we have, in order to find out what the molecule looks like, we have to figure out how many electrons there are in the molecule. So we have 2 carbons that have 4 electrons and 2 chlorines that have 7 electrons each. And that equals 22 electrons total. So we're going to start off with the carbons as essential atoms, and they're bonded to one another, and each carbon is also bonded to a chlorine. And because carbon likes to have 4 bonds, we're going to have a triple bond between the carbons. And the chlorines each have 3 electrons, creating, or 3 electrons pairs plus the bond, creating an octet. And with the Vesper diagram, we need to include the bond angle, which is going to be 180, and also the molecular geometry, which is linear. So the reason for the bond angle is the bonding pair to bonding pair repulsion. And here's just a little picture of how the Vesper molecule would look like. So we have the chlorine bonded to a carbon, and then the triple bond to carbon, another carbon, and a regular bond to chlorine. So the valence bond theory has to do with the energy of the electrons and the way they bond together. The electrons from the different atoms bond together. So we have 2 central atoms, which is each carbon. And the carbons contain 4 valence electrons. So we'll start off with the first carbon. It has, in the 2s orbital, and 2 valence electrons in the 2p orbital. And then, so same for the second carbon. And so when the carbons are in an excited state, the electrons get excited. So one of the electrons from the 2s orbital gets excited to the 2p orbital. And here we're going to have, so it's going to be 1, 2, 3, 4. Same for the other one, the other carbon. So this movement of the electron from the 2s orbital to the 2p orbital is called promoting. And when we promote an electron, it requires energy. So then we need to hybridize. But first, let's go back to our Vesper diagram. So we have the 3 bonds, the triple bond between the carbons. So one of these bonds is going to be a sigma bond, leaving the other two bonds, this one and the one under, they're going to be pi bonds. So because of that, we're only going to take an electron from the s orbital and one electron from the p orbital, which creates an sp orbital. And then the leftover electrons are going to be in the 2p orbital. So the 2 pi orbitals are going to be, or the 2 pi bonds are going to be the bonds between the carbons on the 2p orbitals, between the electrons on the 2p orbitals of the carbon. So this creates the pi bonds. And then the sigma bonds between the carbons are going to be the electrons from the sp orbitals of both carbons. So that's what creates the triple bond. And then the bonds between the carbon and the chlorines, they both are sigma bonds. So these bonds are going to be the bonds between the chlorines, the electrons on the chlorine of the 3p orbitals and the sp orbital of the carbon. So that's what creates the sigma bonds between the chlorine and the carbons. So just a brief little recap. This is the pi bonds are going to be these red little orbitals, and the sigma bond between the carbons is the gray one. And then again, the pi bonds is going to be between, or the sigma bonds are going to be between the 3p and the sp orbitals of the chlorines and the carbon. And yeah. So now let's move on to the contour diagram. So our molecule is linear, and we have the carbon bonded to carbon. So these bonds are bonded between the sp orbitals of both carbons. And here's the 2 electrons in the middle. So these are the sp orbitals. And that bond is a sigma bond. Then the carbons are bonded to the chlorines through the sp orbital. They're bonded to the 3p orbital for the chlorine. And again, this is a sigma bond. Then on the other side, so now we're going to get to the pi bonds. So the pi bonds are the p orbitals, like this, on each carbon. And each p orbital is going to contain 1 electron. So we're going to have 1 on this one, and 1 down here. And again, 1 up here, and 1 down here. So this is going to create the pi bond. So that's 1 pi bond, both of these together. The next pi bond is going to be this one and this one up here. That's a pi bond. So we have 2 pi bonds and 3 sigma bonds total. And now we need to include the the molecular geometry, which is linear. And the bond angle, which is 180 degrees. And then just again to make it a little bit more clear, this is one bond, one pi bond connected with this one. And then this is the other pi bond. Connected with this one down here.